Hey everybody, MoNaCo here, our third glorious unit of study. We're going to start talking about the periodic table. And I'm going to start throwing in little Easter eggs for you in every video. This first video, the Easter egg is this. If you sign up, sending a text message 716-312-6359 with 359 with the message at MoNaCoP, I will give you a STEM buck when you show up tomorrow after you've watched this video. Ask me to check my remind.com. I'll see your name in there. I will give you a STEM buck for signing up for my text alerts, okay? So that's an Easter egg. You're going to keep your ears and eyes open for Easter eggs in each one of these next 10 videos in the unit, because each one means there's a little something in it for you if you come to class having learned about the Easter egg or done what I tell you to do because of the Easter egg. It's a little bit of a carrot on a stick, if you will. So now that I got my soapbox out of the way, we're going to talk about our first homework video, the history of the periodic table. We're going to understand the modern periodic table has changed over time, just like the model of the atom has. And we're going to name the scientists that credited with those major advancements in that periodic table. So let's check it out. All right. So were all of the atoms originally arranged? How were they arranged? Well, originally, we didn't know about atomic number, so we knew about atomic mass. We knew how much hydrogen weighed. We knew how much everything else weighed relative to hydrogen. So the periodic table was originally set up by atomic mass. But after that, nowadays, we're governing it by the law of periodicity, and that's what we're going to talk about today. So periodicity is the history of the table, and this guy named Dmitry Mendeleev, he was a Russian chemist, a professor at the University of St. Petersburg. He was the first one to put the elements in any form of table according to their masses. And you can see here, hydrogen was 1, lithium 6.99. As you go up, the masses, these numbers here, are the masses of the elements, the atomic masses, that is. Okay, so he originally set up his table like that, atomic mass. It resulted in gaps. You can see here that there's some stuff missing. You know, calcium all the way jumps to titanium, zinc jumps to arsenic, okay? There were some gaps in the periodic table. What was important about Mendeleev's table was the fact that he predicted the masses of unknown elements. So he said, I don't know what's in between calcium and titanium, but I bet you that there is one element that goes in there, and its mass will be between 40.1 and 47.9. That was his big contribution. So as a result of those gaps, the thing was out of order. So the periodic table was the first step in the right direction, but it wasn't quite where we know it as today. This guy named Henry Moseley, he was English, sometime afterwards in the 1890s or so range, he uses X-rays and the spectroscope, the same type of thing we did in our flame test lab, to prove the existence of the proton. And since he knows the protons existed now, he realized that every different element had a different number of protons, which he called atomic number, or the number of protons. And so he set up the table by the atomic number instead of the mass. This proved to be much more effective. If you look at any periodic table and start in the top left corner and start reading it like a book, each step along the way, you're going to see one of the numbers in the box, no matter where it is, because each one has a slightly different arrangement, you're going to see that it goes up sequentially, means that's in order. And so here we go, all the way up to 11 and 12. So that's by atomic number. That's how we recognize the periodic table today. There's no more gaps. Well, there's no more gaps because everybody discovered those missing elements that Mendeleev talked about, and now it's filled up all the way up to 100 and 118 now. An octium is the 118th element, which only exists in scientific research laboratories, so we can't actually see it. So the periodic law, this is what is governing how the periodic table is arranged now. It's saying that there's periodic functions, the elements, the properties, periodic functions of their atomic number. A periodic function means something like this. It repeats. Every week is a periodic function. It starts on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, boop, repeat, Monday, Tuesday, Wednesday. So it's a periodic. It starts over again. And they're saying that the atomic number determines what the properties of the elements are, and therefore the properties repeat. So as you move across to a row, or a period, there's a synonym there. We call them rows or periods interchangeably. You add one proton to the nucleus of each atom and one electron out into the valence shell. Okay, so that's one of the periodic functions. Add a proton each step and one electron each step as you move. The maximum number of valence electrons any element can have is 8. We call that an octet. Therefore, any element with 8 valence electrons marks the end of a row or period. If you look at the noble gases, group 18, all of them have 8 valence electrons in the outside shell. Okay? So as we start over, we start onto the next row, next line, kind of like next line of text with 1 valence electron, and then we add 1 as we go. 1 more, boom, as we go, as we go. So you think away Sunday marks the start of a new row on a calendar and just starts the weekly pattern. The number 8 valence electrons ends the pattern in the periodic table, and it starts over again on the next row. The number of valence electrons tells the number of bonds an atom and element can form. So therefore, the number of bonds a form is also a periodic function. The number of bonds an element can form dictates that element's chemical properties. So these electrons being arranged in this way has everything to do with how atoms and elements interact, and they are periodic in nature. So as you move down a group or a column, there's another word, it's called family. So group, column, family, all synonyms. You can add one more principal energy level. It's like another layer of electrons around the outside, another shell, another peel on the onion, if you will, okay, or into that electron shell. All elements in the same column or group or family have the same number of valence electrons. So if you look at a vertical stack of elements on the periodic table, they all have the same number at the end of their electron configuration. Therefore, elements in the same column or group or family tend to have similar chemical properties. They react similarly. Sodium chloride, lithium chloride, potassium chloride, rubidium chloride, cesium chloride, and francium chloride all would have very similar chemical properties in terms of who they react with in other elements. Okay? So that really is it. I know I talked fast. You can pause, rewind, and look back at the video. So now you should recognize that the modern periodic table has evolved over time, and the scientists and their contributions to the periodic law. There are some relative practice packet pages, pages 1, 14, 15, and 29. So you should be able to do those by yourself now. And remember, the Easter egg is to text me with this message at MoNaCo P to get yourself a STEM buck. Make sure I come and check your, make me check my remind.com, and you'll be good to go. Thanks, everybody. See ya.